Okay, hello everyone. Let's start now. Today we are very happy to have invited Congyue here to give a great talk about her great work. Congyue is a postdoc at MIT, working with Bill and Marine. She obtained her PhD in computer science from Stanford University, advised by Bill. Her research interests include 3D computer vision, geometry deep learning, and physical representation learning. In the short term, she aims to integrate geometry representation learning into generative models to better capture the low-dimensional manifold structure of data distributions, with a particular focus on applications in physics and robotics. In the long term, she seeks to uncover geometric structures from data to inform the design of neural networks. Now I'll pass the floor to Congyue. Welcome.
Yeah, thank you so much for the introduction and also for inviting me here and also for the free food. I guess it's pretty nice. So I'm happy to share about some works and maybe also some thoughts here. So it's more like open discussion style kind of thing, and I hope it can be fun. So today I'm gonna talk about this topic, learning representations for generalizable robot actions. Because wait. It's in the afternoon. I guess like probably after lunch, people need a little bit of break, so we can slowly get started with some easy things. So we see like probably everyone are familiar with things like this, like in computer vision. So we have a lot of these very well-known representation features like feature extractor networks in computer vision. Everyone is happy about them. So when we look at these features, like how like we feel like these features are good and many of us like use these features for a lot of applications. So when we look at features like this, like how can we say like they're good? Like why do we feel they're good? Also like here are a little bit more visualization. Like you somehow see like some like correspondences or important regions for discovery of objects from the features, and these are part of the reasons why we feel these features are good. If we think a little bit more, like what are the meaningful things in the features? So there's this like one interesting discussion between the student and the professor at CMU. So someone asked like, what are the three most important problems in computer vision? And the professor answered like correspondence, correspondence, and correspondence. So I mean, there are some people feeling that almost like all perception problems in computer vision, at least like on images, can somehow be abstract as correspondences. So, for example, for semantic understanding or like segmentation or depth estimation, if you have the correspondence in the most generalized sense, like you can transfer the understanding or the information from one image to other images of similar senses, and you can like do correct labeling on top of that. So, if we look back to the features. We also visualize a lot of correspondences like this. Maybe a lot of people have been using the properties here. So we do see like very good correspondences in these features. Like the even things like across different categories or across different styles of images. And of course, like directly using the correspondence for the information feature is one thing that probably like people care about, but also like people care about actual tasks. So people attach prediction heads on top of the features, like for example, a head for predicting depth or a head for predicting like instant segmentation or the semantics of the images. So these are like some different ways of using the features. Like we either directly use the features to directly extract the relation between images or between image patches, or we attach hats to the features and we do good predictions. And all these things are somehow based on our feeling that we feel the features are somehow good. It's capturing some important information for vision, and we can use the features very well for our tasks. So these are just like familiar things in the field. So, but today, like it's like a talk in robotics. So then naturally we have the question, how about representation for robotics? So we have these very good representation learning paradigms in computer vision that help us a lot. So it naturally extends to the question, can similar representation learning paradigms be designed for encoding actions and interactions for robotics? And different people had different answers. So specifically in today's talk, the scope is more going to be limited to imitation learning. So the reason for this is that we want to start with the topics that are closer to the setups in computer vision to make this analogy. So if we think about computer vision, it's like you have some training data, either a lot of data or some training data. You train some network on that. You train a feature extractor there, and hope to get some very good representations there. And you also hope that then like you test the network on some test data and you get some like similar good properties or some generalization. So specifically in the sense of imitation learning, we're also somehow hoping that we train some networks on some data, and then we apply it to some similar scenarios or with certain level of generalization, and we also hope to get something here. So I guess like this is a good setting for us to start with the analogy between learning representations for static vision things and robotic setups. And a little more, so also like a lot of people are talking about the word VLA nowadays, like we have vision, language, and action. These, if we think about these things, like all these components are indeed like important things in robotics. Like you need vision for perception to really understand what your environment or the scene is like. You need language usually for instructions, like understanding what a human actually want a robot to do. And finally, you need the action, which is like the essential part of the output of most like robotics work. Like you need the robot to actually do something. So if we look at these things and we starting with the computer vision things, maybe as an analogy sense. So we have all these components. So back in the days, people first try to do some representation. People first try to have that, for example, I mean, from the computer vision community perspective, people first like have like these vision representations in the latent space, and they seem to be pretty good and help a lot of things. And later people started to add like a little bit more like sauce of multimodality. So people had this joint embedding between vision and language. And in addition to trying to encode the relations or the information of images themselves, people try to mix the information of vision and language together and try to study the relation between these two different things. And so nowadays, like we're trying to add one more thing into the latent space, which are the actions. So the first question is about, so how can we represent actions efficiently in the latent space? If we think about how people try to represent vision and language in the latent space, there were also like a lot of efforts of representing these things or encoding these things in different ways. So the first question is like, how about for actions? And the second question is that, so now like we really have a lot of things in the latent space, so we added like a lot of different flavors into the pot, and we have vision, we have language, and now like we further want to add action. So is the latent space like too full, or like we have so many things here, like how can we coordinate the relation between different modalities here? I mean, again, like I hope this is more like an open discussion here today, so a lot of people have different opinions here. And specifically, I want to start the discussion using some of my past works. So specifically, I want to introduce some of the works here. So going from left to right, I'm going to introduce some works about like representing features for robot learning. So specifically, I'm going to talk about object-centric feature guiding robot actions. And then I'm going to talk about joint features between objects and effectors. And finally, I also want to say, like, for representing actions, how can we understand such encoding in different ways? If we look at this, like, from left to right, it's more like a spectrum. So it's like from the left, it's more like we want to directly learn the lesson from visual representation learning. So we either directly use some good features in computer vision, and we hope that they also help us in robotics, or we directly use some representation learning methods in computer vision, directly applying that to robot data. So does that help us? And towards the left is more talking about, so still, but at the end of the day, like actions and interactions can have different natures compared to static visual perceptions. So given that this is like a kind of a different problem, so in addition to just directly making analogies to computer vision problems, what are the different things, or what are the complementary information that we want to consider in the representation of actions? Okay, so we start with some direct things. Okay, so very straightforward thing. So as shown at the very beginning, we have a lot of representation learning things for visual features. So again, we can still have these features, like we can do exactly the same thing of learning object-centric features on the object point clouds. So here is like more like using a compressive learning kind of thing on some like scene environments of like potential interactions, but purely on the point cloud perceptions. So this is actually like a scenario of like covering the object with a piece of cloth. So you just like have the perceived point cloud from the sensor, and you can do representation learning on that, and you can learn good features on that. And this is a standard compressive learning on point clouds. Like you do like match points as the positive pairs and the non-match points as the negative pairs. And also we have some geometry here, so we added equivariance into the network. And here are the visualization of the features. So if you see like the visualization feature, you do see very good correspondences. Like for things of the similar states and the similar regions, you can observe like after PCA, the features look very similar. And for different states, like the features are kind of different. So Again, things here are still quite as expected because representation learning, all these things like the geometric deep learning or like contrastive learning are well-studied things in computer vision. So you just like apply it to point clouds. People also apply that to point clouds in the past. So it's kind of like as expected. Like after visualizing the features, it should be some good features if the network is trained well. And on top of features, and then like a very straightforward question is like, on top of the good features, can we directly use that to help with robot actions? So on top of the features, we train the policy network on that to learn the policies. Again, imitation learning. So you kind of like learn the distribution of the demonstration trajectories. And also like the policy network, we actually also have some geometry in that. So we also have equivariance. But essentially it's like we use these very nice features learned from like the visual perceptions, and we want to use that to guide the policy networks. And what can we do here? So naturally, we can have some generalization in the task variation. So we inherit the good feature, the good properties in the visual features. So specifically, what we can achieve here is that, for example, from a few human demonstrations, here we didn't analyze a hand specifically with this work, but we use marker to mark the end effector position. And we can directly transfer the policy to similar objects of similar classes, but different different geometric variants, where also different colors, different textures, also different environments. Again, like things here are still kind of like as expected, because if you look at the generalization here, it's mostly at the object variants, like different object shapes, different texture kind of thing, or different poses. But all these things are very object-centric things. And as mentioned before, we already did some visual representation learning on the object-centric features. So as expected, on the features on the objects, they should naturally have those correspondences or those good properties as in computer vision tasks. And then like directly on top of that, we train policy networks. And so the generalization is pretty much inherent from the visual features themselves. And a little bit more comparison of the objects, like the objects for demonstration and some target objects we did for actual manipulation tasks.
Yeah. I missed it maybe earlier. How do you find the ground truth correspondence to train these visual features? Is it self-supervised or?
Oh yeah, that's a very good question. So yeah, I do miss some details here. So specifically in this work, we did some simulations, and in the simulations, we so first of all, in the simulations, like we have the ground truth like correspondences, because like we have the mesh and we have all the correspondences, and in addition, like so basically this is for the correspondence across different like shape variations, and in addition, we follow the point contrast paper, like doing contrastive learning on point cloud. So specifically, for each point cloud, you can simulate the sensor to take like depth RGB images from that like in different angles, and you get the partial point cloud of that. But because like the partial point clouds are simulated from the full point cloud, so you still have the correspondence. So by doing this, like you can kind of like learn the correspondence of like kind of like different views and also different shapes. Yeah, that's only to sim, and we directly apply that for real. But sim is for like the pre-training of the features. So we use a sim to pre-train the features, and we use real demonstrations to train the policy. Yeah. So in addition to that, we also so beforehand that was more like a standard point out kind of thing, learning the policy. So on top of that, we also did like diffusion policy version of this, and we show that with all these good properties in the latent space, we can have like data efficiency and better generalization. So specifically, we show that in similar scenarios, we can use less demonstrations to achieve like still better performances. And here are some cool demonstrations, like in the Stanford Robotics Center in the basement. Like some of them look pretty cool, I guess. Okay, so a very brief summary here is like again like there are a lot of specific designs about the policy learning here. Also like a lot of engineering we did in the work, which I didn't show here. But at the very high level, I just wanna getting started with about the discussion here by emphasizing that so we adopt the good things, either directly adopting the features in computer vision or adopting the feature representation learning paradigms in computer vision. And we use that to learn features still on the perception, like the object point cloud. And we use that feature to guide the policy learning, and that is very helpful, which is kind of as expected, again, from the high level, because the features themselves have very good properties in the visual correspondences. And also like a lot of people are also like adopting the features. So this is like some other work actually from a group at MIT. So they're using the distill feature fields. So basically you have images taken from different angles of the scene and you extract features from the images and you somehow back project and aggregate them to the 3D scene. And you can use these features extracted from the visual perception networks to help you to guide the policy. And here when they use the feature, they also the feature themselves also contain some language information, for example, clip features. So they can also use it to do language guided manipulation under the guidance of the features. So on top of the work, so on top of that work from MIT, so we did a little bit more extension. So we're thinking, so in addition to considering a gripper, how about we also consider like a dexterous hand? Still, like, can we also do some dexterous grasping, following the guidance of those features? So specifically, we did this work where like we also construct the still feature fields, but we also like try to map it from sparse fields instead of like the dense fields like a nerve, and we try to do one-shot manipulation transfer of dexterous hands on top of the features. So a little more. So here are where we did the feature distillation, but we improved that a little bit by like considering sparse fields. So on top of the features directly extracted from the images from a pre-trained encoder, we further did some like 3D compressive learning to further refine the features, and then we also did some pruning and aggregation to polish the features to make them more consistent in the 3D. And with these features, I mean, but again, like all the features here, they're pre-trained from some pre-trained image encoders, and we're refining the features again using some standard techniques like point contrast or detail pruning techniques to make them better, but still like strategies kind of from like computer vision prior works. And on top of that, we did some transfer of hand poses in the feature field. So specifically, suppose like we have a scene where we have the demonstration of how the hand can grab the object. For the points on the dexter hand, we can sample the features. The features of the scene on the surface point of the dexter hand. We can compute like the all those features. And in the target scene, for whatever hand pose, like a candidate hand pose, we can compute we can also like compute all the features on the hand surface, and we can compare the features on the hand surface between the source demonstration scene and the target scene. And then like for this, we can define an energy function in the latent space. And using this energy function, we can do any factor optimization in the target scene. So here, like this is a trajectory where we optimize the hand, essentially like arriving at the position that is like grasping the object similar to the demonstration. So also like here we did some like little interesting experiments. So you see like, for example, here in the scene, if you only have this one point, which is different from the demonstration, but they're kind of from the same class, I'll try to grasp the toy again at the back, similar to the demonstration. But if it's in the clutter scene where you have both this like pink bear toy and the monkey toy, because the monkey toy better match the demonstration, so I'll try to grasp the monkey before the pink thing. So I mean, again, but these are still kind of like the properties inherent from the visual features. But we're now like on top of the features, we're considering a little bit more about the action learning side, where like you're thinking about the poses for the articulation of the end factor itself, because now we're thinking about like the end factor no longer being like a single gripper, but you're thinking that the end factor itself will have some complex geometry. And here are a little bit more demonstrations. So we show some one-shot generalizations where we transfer from the demonstration pose, hand pose to some target scenes, and we can see like some generalization under object shape changes for deformations for like cluttered scenes. Okay, so before going to the next work, like just a very brief summary. So we talk about like using visual features to guide the learning of policies and actions. And we see that the visual features themselves, we can use them in good ways. They can be very, very helpful for learning robot actions because the visual features themselves carry very important information for guiding the action. And going from the very beginning to here, like at the very beginning, we're putting a lot of focus on the scene and the objects themselves. So we're only thinking about grippers, the energy factor being grippers. So we're like you're mostly considering, can you place a gripper at the right place with the right guidance of the feature? And slightly we're shifting to the like dexter hand where we want to emphasize that the robot itself, the energy factor itself, it can have its geometry, it can have its like complex shapes. So maybe you should like put a little bit more focus on the robot itself in addition to the scene features and the object features. So, but here we're still only using the features of the objects, but we're designing more optimization techniques toward the robot side. And following this line, yeah.
So when you do joint, let's say, let's call it somewhat joint optimization of the scene and the helper, right? What type of task are you able to do which was not previously possible? Or would you say it's just improvement in performance? Or you see some binary that, okay, earlier these methods were not performing that well?
I see. I think that's a very good question. Actually, I think the question can be broken into two parts. So A is that so here after this work, it's actually mostly just like optimizing the features, and then we optimize the policy on top of the features. Actually, the next work I'm gonna say like joint learning of the action side and the feature side, and I'm gonna actually show that's helpful on top of this. And I think for the second question, I think it's quite interesting. So I guess like here at least like here, in these kind of works, we're focused targeting mostly at the generalization part because like we say that the visual features themselves carry very good generalization, especially if the feature extractors are trained on a lot of like in the wild images, which cover a lot of like different scenarios. So it's more like using that and also getting like slightly better performances. But I do think it's a very good question in general because it reminds me to think like even originally in computer vision at the very beginning, like people didn't believe in representation learning. I mean, people only believe in supervised learning for very very long time, and people say like you train the representation like without a task. Like, why is it helpful? Is it helpful for better performances, which people actually didn't observe at the very beginning, or is it helpful for you to do something new? I think essentially how people found the representation learning helpful in computer vision. I think people started by noticing them having better performances compared to supervised tasks. So that I think at the very beginning, the motivation was like instead of predefining a task, I mean, people say like pre-text tasks or like some pre-training tasks, and people realize like by doing this, you have a better generalized understanding of the whole thing instead of like optimizing just like towards a task. So I think the generalization is essentially a important goal here. Yeah. Okay. So I'm actually gonna talk about like the joint optimization of the features and the actions. So again, like getting back to the work in the first subsection. So we move like slightly from like purely looking at the features of objects to like looking at the ending factors a little bit, but still using the pre-trained features, but guiding the action manipulation. But if we now like getting back to the features, like looking at the features a little bit, like are we missing something, or what are the complementary things we can think about here? So one thing that people observe ever since like a computer graphics or vision literatures of distilling features into 3D fields, people observe that most of the features are only meaningful on the object surfaces instead of in the space. So specifically, these are some of the visualizations of the feature fields in these prior works. And you see, like, although it is called a feature field, where like people use like nerve or Gaussian splatting kind of representations, like ideally it's really like a 3D field. But when you visualize, like most of the density, almost like maybe over 99% of the density are mostly like on the object surfaces. And when you visualize, you only see the meaningful features on the object surfaces. And here are also like some visualizations of feature fields from a very, not very old, I mean, a NERF paper from a few years ago. So I think this is a very typical example because like NERF is really trying to represent 3D scenes into fields. But when you look at the meaningful things in the fields, they're still just the object surfaces. So if we look at the reason why this is happening, like we think about like how we're extracting the feature. So we're getting the feature from 2D images and we're back projecting them or like distilling them to 3D. But if we think about how the pictures are formed, so we're taking photos to get the pictures, and every pixel, I mean, most of the cases of like opaque objects, like each pixel corresponds to one point on the object surface. I mean, maybe like it can be tricky for like transparent things, but I think in most cases it's like this. So like you get a feature here and back project in 3D. If you do the projection and the aggregation correctly, it's very likely that it is something meaningful on the surface. So you're not really effectively like representing things in the near object space. And also, or people directly get features from point clouds. So the point clouds are from sensors, and the sensors are sensing the points on the object surfaces. So we're mostly like targeting at the meaningful features on the object surface themselves. But if we think about the robot actions, like when we look at objects, we look at the object surfaces to understand them. But when we try to interact with the object, the animating factor is actually moving the free space. Even before you touch the object, like your pose, like it can still be something meaningful about your intention of how you want to interact with the thing, or how you're approaching the thing, or even in some navigation problems, like moving in the free space itself is a meaningful thing in robotics. So the first question we want to think about here is that can we also have some meaningful things in the free space that are not like directly the pixels or the points on the surface that you perceive in your perception networks. And the second question here is also about, because we're thinking about actions and interactions, like the interpoint relations are very important here. So instead of only looking at individual points on the surface or individual patches in the images, we also want to think about the interactions or the intentions or the relations between different things instead of like only that thing you see. So now we're actually trying to going like along the axis, like we already like think about a little bit more complexity on the end effector itself. So why don't we just like move a little bit more forward, saying that instead of encoding the features only on the object surfaces and only view them as visual features for perception and for guiding the policies, how about we just represent the features between the objects and the end effectors, following the previous question. So from the previous work about the Dexter hand, we did a little more extension towards this direction. Where like beforehand, we were considering a feature field, but it's mostly like features on the sim points, so like the surface points. And for when optimizing the Dexter hand, for any point on the hand, which is like in the space of the surface, we do a L2 distance guided interpolation, and we compute the feature there, and we optimize the hand, essentially because we're assuming that at the end of the day, the hand will land on the surface. So after the optimization, like essentially like the optimal point of the optimization should be all like with the surface features. So now we're saying like, how about like instead of modeling the features of the individual points on the object in a purely object-centric way, how about we model the relations between the object points and the hand points? So we're proposing this neural attention field where we focus on this we call like second order information, which is mostly encoding the information between the object points and the hand points, and we directly use these attentions as features instead of individual features on objects to guide the learning of the actions. So here's a little bit comparison. So we still want to do this one-shot demonstration to like some other scene like manipulation kind of task. And here is mostly graph speed. But instead of like using the features, we're saying like, can we focus on modeling the attentions between points instead of the individual features of the points?
Yeah. But I thought, so maybe I'm not getting it. Transformer decoder is basically an attention, or is it a, so what would be the main difference between the first one and the like feature field and attention? Is it just the additional key and value heads? Because that's the only, I guess, difference I can see between the first point and the second one, where you might project this new point into keys and values.
Oh, I see. Yeah. I think it's a very good question. I think first of all, like a small clarification here, because like there are so many terminology about transformer nowadays. Like there's like transformer decoder, like decoder only transformer. Like also like in PyTorch and like a lot of literature, like the transformer encoder and decoder refer to different things. But here it mostly refers to cross attention. And also I think it's a very good question. So I think here like in this slide, so basically it is like instead of like doing a sim point. So basically here is like you have the features of the sim points and you do L2 distance kind of interpolation. Kind of like a Gaussian kernel or Gaussian splatting kind of style. And you interpolate that to get the features on the hand. Here is like we're computing the cross attention between the sim point and the hand points. Intuitively it sounds like just like replacing the interpolation with the transformer. In practice it is how it is implemented. Yeah, but later I'm gonna say like how it is trained and why this is like encoding like information like that. So yeah, I'm gonna first talk about inference, which is like exactly as you said. Like so basically here are the sim points. So you have the sim points here, and here these are the hand points. So like you see like this point is like here influence a token, this point here, here. And like you have these hand points and you go through the transformer and you directly get the output feature for like you get the output tokens of all the hand points like through this cross attention. So like when you get these output tokens, they naturally carry the information of both the hand and the scene, and actually like the attention between them, like which like for each like point on the hand, like which region of the scene you should focus on. And using these output tokens for both the source point cloud and the target point cloud, we can compute an energy function. And based on the energy function, we can do hand close optimization. So this is still the optimization trajectory where essentially you want to grasp the region you'll see, which is like similar to your demonstration. And specifically here, one difference in the inference we want to emphasize is that beforehand, it's like you can pre-compute all the features on the scene, and at inference time, you just interpolate them and do the optimization. Here's like in the optimization process, like through the entire line of the optimization, at every single step of optimization, you need to go through the transformer to compute the relation of the scene. So basically, in the optimization process, you're iteratively updating like which region of the scene you want to focus on to guide your manipulation. And then I'm going to talk about how to train that. So how to train that also kind of interesting way. So because we still want to do one shot or few shot generalization, so we don't want to do say like we have 1,000 demonstrations and we only train this transformer to learn like which region of the scene we want to focus on from the demonstrations. But instead we're thinking like can we extract meaningful things for the transformer from as minimal information as possible? So we actually only train the transformer with simple clouds without any vector handle, without any demonstration. So how we're doing this is that we design this self-supervised cycle consistency loss. So suppose like we have a few scenes directly using the like feature extractors like a dino feature extractor or visual feature extractor, you can first get a very coarse correspondence across the scenes. So so basically, beforehand, like when doing inference with a transformer, we're using that to compute the cross attention between the hand points and the scene points. And here, like at the training time, so for both directions in the transformer, we all input the scene points. So we compute the self attention between the scene points. And we're saying that after this transformer, like after updating the scene point features themselves, they should be self-consistent. So like they should preserve all the cycles of correspondences across like the few scenes. So how can we understand this? Is like we're assuming that you have an object here, and you're actually like placing a virtual grouper at the single point on the scene. So it's like suppose like two objects naturally have visual correspondences. If we think about the first line of work using visual correspondences to guide the manipulation, like supposing that you put a virtual grouper here, the virtual grouper should also preserve the correspondence between the two objects. So here we're using this self-consistency to train this transformer decoder, which we directly apply to the vector hand for manipulation. So one thing I want to emphasize here is that using this self-consistency, this training itself is not introducing any additional information. This is just using the information in the visual features from the visual encoder. But we're going to show that even without introducing additional information, just using this way to reorganize the information, to push the information to be interpreted in a way that is more kind of like action-centric or relation-centric, we can give you better optimization landscapes for the action learning side. So after that self-supervised training, we compare this to the interpolation itself, and we can see that these are the energy fields. So this is the energy field purely from the feature interpolation of the visual encoder, and this is the energy field after applying this transformer. And you can see that after this transformer, like the high relevance regions are much more centered around the actual regions for the manipulation. But also beforehand, you see like there are a lot of like random like energies in the empty space, but here like many of the most regions of the empty space are like excluded in the like energy field. Yeah, and here are some generalization experiments. So we see like by doing this like reorganization of the attention like, from the visual features, we see that we can have better generalization, especially in clutter scenes, especially like your distractor objects are very close to your manipulation of the interaction point. And also like it can have better generalization in some cases. So here again, I want to emphasize like we're showing that you already have those very good visual features. In the previous section, I showed that you can directly use it to guide the learning of the actions and interactions, and it's very helpful because they're very useful features. But here we're saying that even without introducing additional things, but you only have these features, but by focusing on the interaction instead of the visual perception, so by reinterpreting the features in a way that focus on the interpoint relations instead of individual point features, you can already get better actions here. So yeah, so this is saying that so for learning the representations or using representations for action learning or robot learning tasks, we can respect more about the action side or what are the important things in actions like the interactions between points, and we can organize features or focus on the such properties in the features and use it to better help our task. So speaking of this, we're gonna like move a little bit more forward toward the axis. So we're saying that so we want to have features that are more action-centric or better focus on the ending factor and the interaction between the ending factor and the objects instead of only looking at the objects. So how about we think about the problem also from the action side instead of like directly making analogies to the vision side. So what are the important things in actions? For example, here we said relations. So what are these things that we want to have in the latent space, in the representations to really help us with the tasks? So getting back a little bit again, so we had a lot of representations. As I mentioned since the beginning, we have all these very nice visual features, for example, images, and we say they have good visual correspondences, and it's very helpful for us. And we also have some very good features from some other CADs or some other fields. For example, in NLP, like originally people had the word to back, and people visualize those things in the latent space, and people see these very good semantic relations. And also, like in geometric deep learning, people develop features that respect geometric transformations. And all these features, they're helpful for these different tasks, like in their scenarios. So, and also, like when we look at like many of these representation learning frameworks, we'll see that, I mean, sometimes they share some similar high-level senses, but how specifically people design the network architecture, the losses, and the pretext tasks are really different. So people are trying to design these representation learning things like by respecting the important information in these different tasks. And then comes to us, like we care about actions and interactions here, and what are the important things, or what are the possible things we want to represent in the latent space, especially in addition to the visual perceptions. So what are the complementary things that we want to take care of here? So one important thing is, of course, is actually actions. So to break it down a little more, like what exactly do we want in an action representation? So actually, I like this example here. So I don't know if you guys like know of like blenders like this. So this one is actually a blender, and you have a container at the top. You put some fruits into the container. You press the container, and it will give you the thing. So if you think about the container part, especially like there are a lot of like LLM guided manipulation works. So if you think about container part, like by we're speaking natural language, most time people say like there's a container, it's a container part. However, if you think about the action, when you execute this like action, you're actually pressing the container. So the action itself is more like a pressing button action. So if you purely look at the action or the interaction between the ending factor and the object, you may try to, I mean, the better way may to call the part a button. So if you think about the semantics and the action of the part, it can have different meanings. And probably in the latent space or like in representations of actions, we want to consider like both aspects of this. And going back to some very old literature of Gibson theory of affordances. So because like affordances was one of the early ways like people describe how humans have intentions of interacting with objects. And now we're thinking about how robots can have intentions interacting with objects. So when we think about affordances, so there are many different types of affordances. And also like in the old literature, there's a notion of mixed affordance, where it says like when you have intention interacting with an object, it is like guided by a few different aspects. So one example following the blender example is also this one, I mean, from the affordance literature, is that, for example, the mailboxes is a very good example of mixed affordance. So if you think about a mailbox, you will drop mails into the mailbox. And the physical aspect of that is that you know it is a box. So if you drop things into the box will contain the object. I mean, also in a lot of affordance data set annotation, people will annotate contain in the box or like hold at the box bottom. But on the other side, you will only drop mails into the box because like you understand the postal system behind the mailbox. So you know this is a meaningful action that will lead you the right results. But instead you tend to not like drop other things into the mailbox. So also like in a lot of language guided manipulation tests nowadays, we actually also hope the robot to do similar things. On one side, you wanted to do some physically plausible things that can actually interact with the physical world. On the other side, like you wanted to actually understand your language instructions to do some like smart moves instead of like only like doing random things there. So we do want potentially like in the action representation to respect both aspects of that. And getting back to the blender example again, so like for each part, we can have the semantic part understanding, which is like how you try to describe it, describe the semantics of that. For example, you call it a container. I mean, also potentially because it has a affordance of the contain. And on the other side, when you actually care about the action that you're going to execute, you probably want to call it something like a button, or you want it to focus on it being a button. And maybe when you do some retrieval or some correspondences, you want it to be you want its representation or its relation to be closer to other button things, so you can actually use the actions there better. So specifically based on these understandings or these intuitions, we use LLM to build a system to decompose like a lot of like home appliances and their part understandings into these this twofold and affordance understanding of the parts. So specifically, we use programmatic representation for all the objects where you have like many parts there, and you have the part graph, and you have the twofold understanding of each part of the object. And for example, for the blender again, so for the semantic part, we call it a container, and for the action part, we call it a button. So we kind of like use an LM to like decompose all the objects into that aspect. And on top of that, we can use that to generate actions, where we also have like actions like following these programmatic like executions. And there are a lot of like engineering details here, but basically it's like following the high level intuition there. And also like this is an example like maybe like some of you have been working with, so like one of the panels for the robot arms. So if you look at the panel, like the red thing there, it looks like a button. So a lot of visual systems where you apply some like VLM there, will first try to identify that a button. So like in our like whole like system thing, you'll first try to execute a button policy there, try to press it, and then you will realize it's actually not a button. So because like physically you didn't succeed. So then like we'll say like, are there other interpretations? And then we'll try to like turn it as a knob. So like it fixes the physical understanding of that. So basically here I just want to say like by disentangling the physical understanding and the semantic understanding of all the object parts, you can probably build a system on top of that to respect both aspects. Okay, getting back to the summary, also we're almost running out of time, I guess. So a brief summary of today what I talk about. So we had this axis about representations for robot actions. Specifically, we go from left to right. We went from the more computer vision side, where can we directly borrow the visual features from visual encoders or the visual representation learning paradigms to apply it to guide the robot policy learning. And towards the other side of the axis, we're going more towards like, but essentially like actions and interactions, they have different natures in their data and in the task problems. So what are the complementary things or what are different things we also want to address in addition, or that are different from the visual representations? And a little bit more about other things. So what are the things I didn't cover today? So again, like remember that at the very beginning of the talk, I mentioned that. So today we want to mostly focus on the scenario of imitation learning, which is a text setting that is like most analogous to like computer vision things. Like you have some training data, you train something there, and you have some new test cases and you want to apply there. And based on, I mean, the distribution of the training and the test data or the amount of training data, you have different like test difficulties or different things to tackle there. And so we're mostly like talking about like a similar setting like that in robotics, but the actions being a different format of things compared to vision data. And but in addition, like in robotics, there are also some things that could be fundamentally different from like how visual perception networks are trained. So for example, we have the dynamic world and physical simulators. So we actually have these dynamic environments where you can do explorations. So you can try different things and see your outcomes. So here, like maybe there could also be some important representations, like learn from these active processes instead of like just like passively acquiring them from the data. And at the very end, I just want to go back to the comics. So basically, back in the days, people had a lot of success of, like, for example, adding vision to the latent space, and then adding a language into the latent space where it makes vision and language together to model the relations between them. And nowadays, like people are very passionate about like, can we further add actions into the latent space? And when we talk about that, we think about like how can we represent the actions or what are the important information in the action that we do what we add into the latent space. And also like because now we're mixing everything in the latent space. So how can we mix them? How can we model the relations between different modalities? And the very, very end, I also want to say, so the latent space now really has a lot of things. So we probably do want to have some good understanding or good structure in the latent space. And specifically, we probably do want to address the understanding of the actual physical world to respect the physics of the world. And I think that's all. Thanks.